you kind of get to pick, is this qubit doing compute or is it doing storage? And if you have a computer of twice the size, but the problem is the same size, the amount of storage you need hasn't increased. And the storage is something like 2/3 of the space. And so the remaining 1/3, which was used for compute, all of the doubling is just adding to that. So you went from 1/3 compute to 4/3 compute. And so there's a sense in which doubling the size of the machine, you expect it to run 4 times faster. I find that I'm very focused by the fact that I'm on a team that's trying to make a machine that's going to work. This sort of prevents you from completely surfing on the edge because you need to turn it into something that someone could actually do. Like here is the series of pulses you would send to the hardware ultimately. We know that the whole world is described by quantum information. Currently, we can't really work with that type of information, not reliably, not with many, many steps. And quantum computers should fix that.
This week, Misha and Yudong speak with Craig Gidney of Google Quantum AI, whose work focuses on the practical realities of building fault-tolerant quantum computers. Gidney explains why the hardest part of quantum algorithms is often the underlying arithmetic and how seemingly small implementation choices can dominate their cost. We explore the tools Craig's made to help visualize quantum circuits and how insights from software engineering have shaped modern quantum research. Please welcome Craig Gidney.
There are papers that claim they factor 21 with the quantum computer, but I have a very specific test that I apply to these papers, which is did they do the multiplication under superposition? And as far as I know, none of the papers that have claimed to factor 21 have done that. And instead, they've done things that are sort of inspired by Shor's algorithm, where they've replaced the expensive part, which is the multiplication, with something that happens to have the same period, like maybe addition, or in the worst case, like XORing. And if you have to do the multiplication, there's this surprising thing where multiplication mod 15 is really cheap. It's surprisingly cheap. But multiplication mod 21 and most other numbers, you don't get that benefit. And so the number of gates you need goes up by like a factor of 100. And this is one of the reasons that there's been this big time gap between factoring 15 kind of properly and factoring other numbers properly. So you have to overcome this factor of 100 in scale.
Is there an easy way to show that 15 is the...
So you might notice, for example, that it's 1 less than a power of 2. So if I take 8 times 2 is 16, mod 15 is 1. In binary, 8 is written 1, 0, 0, 0, and 1 is written 0, 0, 0, 1. And you might notice, oh, it's the same digits but rearranged. And that, in fact, is always true for the multiplication by 2 mod 15. It's just a rolling around of the bits. They don't actually interact with each other. They just move. And in fact, that's true of every single thing you want to multiply by mod 15, all the coprimes. Some of them also have a bit flip, but none of them have like a C0 gate between the two of the bits. And that's what makes it cheap. Like I'm not aware of any other multiplier for other semi-primes that's that cheap. They all have to say something like, if this bit is on, then this other bit is going to flip or not. Whereas 15, it doesn't have to do that. Other powers of 2 minus 1, multiplying by 2 has this property, but they'll have coprimes that you have to multiply by also during the algorithm that don't have this property. And it would be sort of cheaty to pick the easiest one because Shor's algorithm says you should pick a random base. I mean, you could start by picking 2 just to see if it works, but
yeah. Maybe to sort of broaden this to just the general topic of why is it important to do arithmetics or to know how to do arithmetics very well on a quantum computer?
When you say arithmetics, you just mean like arithmetic operations?
Yeah,
like
arithmetic operations.
They come up in a lot of algorithms. Like even in chemistry algorithms, you end up finding yourself doing additions and like table lookups and little subroutines like this. So because they show up a lot, it's very useful to know how to do them well.
Yeah, and it seems that a lot of the cost of actually running an algorithm on a quantum computer comes from these classical reversible logic. And it seems that the theory paper that proposed these algorithms that don't typically show that intuition, like until later on when you have detailed implementation, then it starts to show.
Yeah, I'm not sure if it's universally true, but definitely most of the things I've worked on, they've ended up dominated by these classical routines. I do think that there are some like physics simulation type algorithms where there's a lot of rotations by weird angles, and they could end up dominated by that process, which can involve doing many gates from a fixed set instead of the arithmetic. But like I said, most of the stuff I've worked on, it has been arithmetic dominated.
There was a number of papers that you've done that concerns circuits like addition, and what was the impetus to look so closely at these specific arithmetic operations?
For the paper in particular you're referring to, which is like halving the
Having the
cost,
cost, yeah.
of addition, I'd been talking with Austin Fowler on the team, and this is early on, and he was just telling me various things about error correction and algorithms. And one of the things he mentioned was that there was no known way to do addition with less than 8 T gates per qubit. So if you wanted a 100 qubit adder, you needed 400 T gates plus or minus a constant. And I was thinking about that, and I have my little tool like Quirk for dragging around gates and just trying stuff. And I found a way to basically, the addition has two parts, which is like a downward sweep and an upward sweep because of ripple carry adder.
Yeah.
And I found a way in the upward sweep to like have one of the T gates come out instead of going in. And so I could then feed it into the next one. And then later I realized I could do better than that by just measuring a qubit in a particular way and doing a correction. And I showed that to Austin, and he was excited by it. And so I wrote a paper, and people seem to like it.
Yeah, it seems like there's a broader context, which is that T gates are expensive in the surface code error correction. So it seems like a lot of these algorithmic improvements, or this implementation level improvement, is like deeply rooted in the fault-tolerant architecture. Have you observed similar kinds of, you can say, leaky abstraction, where these innovations has to be rooted in like the specific details of how fault tolerance is achieved?
Absolutely. So, I mean, actually, when that paper came out, the addition paper, and earlier than that, T gates were thought to be much more expensive than we believe they are now because the techniques for making them were less refined. And as those costs change, it does change how you optimize things. If a T gate is 100 times more expensive than all the other gates, you can basically just count the T gates in order to estimate the cost of an algorithm because they just tend to dominate. You don't really do 100 other gates for every T gate. But now where they're more like, at least in a surface code lattice surgery context, more like twice the cost, something like that, then you kind of have to start considering the other things. And that, yeah, it does change how you arrange things. It changes what's expensive. It changes the optimal points. And when you start considering other architectures that maybe have transversal gates that make the T gate proportionally more expensive because it's not prepared in a way that they can benefit from that currently, then the estimates that they make may look more like the older ones where we were more interested in producing T gates.
Yeah, maybe we could go a little bit broader. Why the T gate plays a special role in fault tolerant or quantum error correction, and then.
So it's very common for error correcting codes to implement the Clifford set in a sort of, let's say, native way. But to have some gates like the T gate that it's not really clear how to do them other than via either switching between codes or by what's called magic state injection and distillation and teleportation. So in the surface code, for example, there are some gates that are extremely cheap. They're so cheap that you don't even really think about them, even in a planar architecture. This would be like initializing a logical qubit into the 0 state or into the 0+1 state, measuring in the Z basis or the X basis, doing a logical Pauli, so a bit flip or a phase flip. And then there are operations that we intend to do by what's called lattice surgery. These tend to take D rounds, where D is your code distance. So let's just say 25 rounds. On a superconducting machine, a round might be around a microsecond. So it's 25 microseconds, where the other operations I described would be more like 1 microsecond. So those gates would be like a controlled NOT gate or a Hadamard gate or an S gate. And then beyond that, there are these T gates, and those we have to do this procedure where we prepare a T state. So you kind of, the way people used to do it is you would physically just make a T state on one physical qubit, and then you would perform an encoding process where you put it into a surface code.
Mm-hmm.
And this is a very noisy process. So at the output, the state is going to have an error rate of somewhere around like 1 in 100.
Why is it noisy to make the T gates?
I see. I wouldn't say that it's noisy. I would just say that there's not a procedure that does it that doesn't involve like first decoding the qubit and then doing it and then re-encoding the qubit, which should obviously be a noisy process because the qubit is temporarily not protected. There are codes that have easy ways of doing the T gate. For example, the 3D color code has a transversal T gate where you just do a logical T by applying a physical T to every qubit in the code.
Mm-hmm.
The surface code doesn't have that, and so we have to go get it via another route.
It's like the downside of the surface codes. That
it is one of the downsides of the surface codes. I wouldn't say it's the biggest one. The biggest one is the space overhead. But like, in fact, most codes, there's some gate that's inconvenient to do. Like there are theorems that not all gates can be maximally convenient to do. They can't all be transversal, for example. But usually there's some gate that's the hard one.
Well, now most of the researchers are focused on, let's say, T gates. How do we optimize them? How do we get them with like high quality? Are there any other candidates, or this is the obvious choice for?
I don't know if I'd say it's the
preferred gates.
I don't know if I say it's the obvious choice. People make other proposals all the time. A very common one you'll see is code switching, where you have some procedure to go from code A to code B. In code B, the T gate is easy. You do it there. Then you go back to code A where your other stuff is easy. Then your cost is dominated by the actual code switching procedure. So, do you need D rounds to finish the code switching? Then you still have a D round T gate. I've generally been kind of skeptical of most papers that start with, oh, we try to do better than magic state distillation, but only because they tend not to end with numbers. Like they tend not to end with, oh, and then we simulated the circuit and we checked how well it worked. They tend to end with, and that's our idea conclusion. And that's an important type of research to do, but most of it is not going to actually work better once you get down to it. And magic state distillation has survived quite a lot of attempts of people replacing it with other things. It has some intrinsic advantages that make this not so crazy. In particular, state preparation, you can use error detection instead of error correction. And being allowed to throw things away when they look suspicious is a major advantage. It's sort of like it doubles your code distance. If you have a distance 5 code and you see something go wrong and throw it out, there need to be at least 5 errors to fool that process. Whereas if you're trying to correct things when you see they go wrong, then you only need 3. So if you have a noise strength of 0.1% gate error, that's the difference between a 1 in a billion error rate and a 1 in a million billion error rate. So these code switching procedures, because they have to use error correction, because they're transforming a state that you can't throw away, that you want to apply a gate to and keep, they have this code distance disadvantage that they have to overcome with some other advantage.
Yeah. So you have built some of the most foundational tools that people have used in softwares for error correction, like Stim and Crumble. Maybe you can speak to the impetus behind developing those.
Sure. I don't know if I would describe them as foundational, but Stim is getting a lot of use. And I'm a software engineer by training, and so it's natural for me to write computer programs and other tools like that as part of doing my research. I would also describe myself as, when it comes to like doing math, as clumsy, and it's very useful to have a computer check what I'm doing so that I don't make mistakes, at least publicly. And yeah, so this is natural. And sometimes they're good enough that I don't just write them for myself, but I try to get them out into the world so other people can use them. Stim in particular was driven by this kind of annoyance that we had with the field that no one was doing circuit noise simulations. they're mostly doing what are called code capacity simulations, which is a model where you have a perfect quantum computer that's sending information over a noisy line to another perfect quantum computer. And they're related to each other, circuit noise and code capacity, but they can be qualitatively very different. For example, the threshold of the surface code is 10 times lower under circuit noise. And so if you're trying to do comparisons between codes, like maybe you'll be off by a factor of 10 if you do it in that model instead of the circuit noise model. There are also additional challenges in the circuit noise model, like the decoding problem is one dimension higher. Like if you have a 2D code that you run for many rounds, those many rounds are like a third dimension. And this can change the runtime of the decoding. It can change the threshold. It can change the accuracy. And it definitely is more expensive to do the simulation because there's just more bits that have to be generated. And because the threshold is lower, the correction is a little harder.
Was there also a point about like human-computer interaction where there's a certain amount of latency that you can tolerate?
With Stim, that doesn't really come up so much. I do have that point in the paper about I don't like waiting a long time for results. Because it's a Python API, you run it, you get the result back. It is very useful to get it back quickly rather than slowly. And there is these HCI guidelines along the lines of, if it takes 0.1 seconds, it feels basically instant. Like it feels like the computer is reacting to you. And if it takes a second, then it feels like you asked a question, you're waiting for the answer. And if it takes 10 seconds, then you go and you get coffee.
Right.
Like you start thinking about something else. So I wanted to enable tools that could hit those lower things by having these simulations be faster. It itself, because it's not like a GUI, it's not like a drag and drop interface, you don't feel this so much. And in most of my usage of Stim, I'm doing enormous simulations where I'll have it running for a week and come back and get the results. It's a week instead of a year, so that's nice, but I don't really benefit from this 0.1 second thing, unfortunately. Yeah.
And it seems like Crumble helps with visualizing a lot of this.
It's like on the GUI side, right?
Yeah, Crumble's more on the GUI side. Ironically, it's not using Stim as its backend because it's not actually simulating the circuits. What Crumble does is it's a tool, it's a circuit editor tool, and it will show you how Pauli errors would propagate through the circuit or how knowledge of a particular stabilizer would propagate through the circuit. Those two statements end up being equivalent. And this is a very common thing when you're designing an error correction circuit that you need to know the answer to. Like, does this error become something bad? Or which way does it go? Or is it the case that this reset causes that measurement to be deterministic? And yeah, Crumble is a tool that I hacked together out of necessity to answer those questions because I was trying to make circuits that were more complicated than I could do by hand, or like even I was writing code to generate them and I kept breaking them as part of trying to fix them. You get stuck in this cycle of, fix A, break B, fix B, break C, fix C, break A. But once I was able to see the circuit and just ask these questions quickly, I could figure it out. It still took, weeks to get that circuit to the state where I was happy with it, but it would have been impossible without that tool, at least for me.
And these days, people vibe code with clock code, and I don't know if
it should be a lot easier to make a GUI like this nowadays, at least in principle.
Have you actually tried some of the coding assistants and see if they actually get the underlying mathematics correct?
I haven't tried a lot. I do generate code sometimes with LLMs, but for my actual work, it's still a little bit too complicated for them in my experience. Like they make little mistakes that have to be fixed. But if you're just trying to like get started on something, like I want to make a plot that vaguely looks like this, or I haven't written Rust and I need to know what a main method looks like that prints out something and reads a file. It will give you that like almost immediately, and then you can tweak it. I find it very useful for that. Anytime I've asked it for a method that I was going to write, I've always had to fix it. I've never, it could, like I know people specialize in like very carefully asking for what they want and doing this iteratively. I currently don't have the patience for that with these tools.
Yeah, sounds like it's good for like this quick things where accuracy doesn't really matter. Just
Yeah, one of the most important things is you have to be able to know if the output is correct. You have to be able to check it.
I see.
If you can't check it, it's going to make something that looks correct but is wrong. You're going to think that it's right, and then you're going to email it to someone, potentially me, and say like, look at this cool thing that I made, and I'm going to read it, and like, this doesn't make sense.
Right. And so what are the main usage of Stim and Crumble that you've seen, where people say, for instance, this is very helpful because I can see, let's say, the detectors and error correcting code, etc.
So I actually don't know how widely used Crumble is. I don't have any analytics on it or anything. I don't, when I run into people at conferences, they don't say, oh, I used Crumble for this. I see a few papers that will link to it as a way of providing their circuit. With Stim, I can see like citation counts of the paper. And when I run into people at conferences, they do say like, oh, I was doing this with Stim. So I think Stim has had a big impact on the field. I think it has made it easier for people to do circuit noise simulations. And I was very happy, in fact, that people started doing more circuit noise simulations, getting kind of a little bit more realistic. So that I feel really good about. Although now I kind of start to worry. There are things that Stim can't do. It's not very good at dealing with like qubit loss, which is a thing that neutral atom machines have to deal with. Because if you lose the qubit, there are certain Clifford gates that don't happen. And the algorithm that Stim uses for sampling does not like a Clifford gate may or may not occur. It is fine with Bahali gate may or may not occur, but Clifford gates, it would be 100 times slower. And another thing it doesn't really do well is anything to do with non-Clifford gates, so like a T gate. Those are things that we want to simulate sometimes. That would be very useful. It also doesn't really do feedback very well. So for kind of the same reason that it doesn't like doing qubit loss, it would be Cliffords that happen differently depending on things that have happened in the circuit.
Do you see the tools coming for non-Clifford gates?
I hope so. I have some ideas, but none of them have been good enough yet to make something. I do think that there's a niche there waiting for someone to make some, cool tool that just solves this problem for people.
Maybe a related topic was what was the journey for you like to learn quantum computing? Because most people, I think, at least I went through like a PhD program, and there's a lot of formal academic training that goes with it.
Yeah, so I went to university for computer science. I have a master's in computer science, but I was never taught quantum computing formally. Well, there was, at the end of one of our algorithms course, we had an extra day, and the professor tried to teach us a little bit of it. Did not stick. In my case, I would say the first thing that I did that was sort of on this path was, I don't know, there's this old blog called Less Wrong. And one of the things that they did on it was they talked about quantum mechanics. And unlike most other popularizations of quantum mechanics, they included, here's the math that you do for a Mach-Zehnder interferometer. And they said, a photon comes in, it can be on one of these two paths. If a path hits a mirror, multiply the amplitude by I. If it goes through a beam splitter, say each path gets a contribution of square root of a half, and the one that bounced gets multiplied by I. I've been told this is slightly wrong from the physics perspective, but it's got the key essence from the quantum information perspective, which is, make superpositions, track their amplitudes, and then you can get destructive interference. Anyways, it was explained well enough that I was like, oh, I can write code that does this, and then I can drop beam splitters and mirrors and make loops and see what it does. And I will say there was a lot of confusion at that point. I didn't really understand what was allowed and what wasn't allowed. So sometimes I'd be like, what if I don't multiply by I when I go through the beam splitter and just both get positive amplitude? You may know that this is very bad. It's not unitary. I didn't know the word unitary at that point. Another thing that I tried putting in my little hacky simulator was a thing that would catch the photon and transition from uncaught state to caught state. And this is also a huge problem because it's not reversible. So it's also not unitary. If you run the simulation backwards, you don't know when to uncatch the photon. And so I was doing all these things, and I didn't really understand why some of them, everything would go okay, and some of them, like the probabilities would go to 0 or like 200% chances of things happening. And what fixed that was seeing a talk by Scott Aronson, where he just had a slide that on the left was statistics and on the right was quantum mechanics. And on the left is like, okay, you have a state vector. There's different ways things can be. They have associated probabilities. The probabilities add up to 1. On the right, it was, okay, you have a state vector. Different things have different amplitudes. Their squares add up to 1. And for operations, on the left, you have things that preserve that the probabilities add up to 1, which are called stochastic matrices. And then on the right, things that preserve that the square adds up to 1, which is called unitary matrices. And that's where, I mean, all of a sudden I could figure out what mistakes I was making and kind of make progress. And like then like learned Grover's algorithm and learned like the Mermin-Prez magic square game. Like I spent a bunch of time trying to understand that, which I can guarantee you is much harder when you don't yet understand what it means to measure X tensor X.
Right.
Like the Wikipedia page has this very excellent summary of the winning strategy for that Bell inequality in a language that I did not yet understand. And so I had to try to figure out what they were talking about and try to solve it. And it was only like years later that I can go back to that page and understand it. Like, wow, that's much easier than having to find I forget what I was doing, like find like a 16 by 16 matrix that had certain properties and like had written brute force code to find it. I had a solution. I wouldn't recommend that way of solving it anymore.
Yeah, I think that's a very interesting story. Like, what would you say to people who are interested in quantum computing and they're trying to figure out a way to maybe break into the field somehow and make their contributions? I feel like you might have some interesting perspectives.
I mean, the thing that worked for me was making these tools and then showing them to people. So, like I said, I joined Google as a software engineer, and I wasn't on the quantum team. And Quirk is one of the things that I showed to the quantum team when I was applying there. Is a clear piece of evidence that like I understand quantum computing, and that, I don't know, an artifact like that was very helpful. I don't know what that's going to mean in the future when you can like vibe code these things. Like it's much easier now for someone to just ask an AI, like, can you make me a drag and drop thing? And that makes it a little bit less impressive. But I don't know how to make it impressive anymore.
It's like higher barrier for the junior software engineers to.
Yeah, I guess there is a valid point about like being able to demonstrate your understanding rather than just print it on a resume or something. I think having a project that you have built and you have very detailed knowledge about, and you can demonstrate that. That speaks louder than
it's also, or at least at the time, it was a lot of work. Like that was like a year of like weekends programming that thing.
Yeah, I feel like these days it's still, I don't think you can vibe code like something like Quirk. I think you can vibe code something that looks like it.
Yeah.
But it won't be 100% correct. Like you still have to know what you're doing.
Check it, but it doesn't have any loopholes.
I'm not sure exactly where it would break because I don't have a lot of experience with vibe coding. I have seen things that people have said, like, I vibe coded this, and you look at it and you're like, I don't know if I like this. I vibe coded a video game and it's like some plane flying around and it doesn't look good and it doesn't control well, but it's getting better. I can talk about some of the technical difficulties behind Quirk, at least at the time. For example, in order to make it fast enough, it had to be running on the GPU instead of the CPU. And at the time, there was WebGL version 1, which didn't have compute shaders yet. It only had what are called fragment shaders, which are mostly used for like drawing pixels to the screen. And so everything is in terms of, the red and green and blue and alpha color components. And so if you like go into the source code of Quirk, it's like, how is it tracking the real and imaginary parts of the amplitudes? Well, that's the red part and the green part of the pixel. And WebGL version 1 didn't have like bitwise instructions. You couldn't extract a bit from an integer easily. You had to do it with floating point arithmetic. So you'd like do a division and a modulus, and all of the shaders have an input that's called secret 0, which is always set to 0. And it's only there to prevent the compiler from doing rounding that it's not supposed to do. And I saw it doing on certain machines. Like if I see it rounding in a way it didn't want, I'd say, oh, that thing plus secret 0. And because it could no longer figure out what the expression was, it stopped breaking it. There's all kinds of stuff like that behind the scenes.
Yeah, I feel like this is the sort of the ground level of like programming where you truly know the details, and then yeah, I feel like with AI it's very possible that people just no longer really get to that level,
lose the skill.
It may become unnecessary.
Yeah.
That's the ideal outcome. Like I have a terrible sense of direction, but I have GPS. 100 years ago, a terrible sense of direction would have been a much bigger problem than it is now. So in a sense, the skill has become less necessary.
Interesting. So, but what in general, like, does it come from your childhood? How did you start? Why did you decide to go towards like software development, software engineering, writing codes?
It started with video games.
Video games?
Yeah.
What was your favorite video game?
Probably Starcraft. Maybe Warcraft 3. They had like map editors that they weren't really programming languages. Well, Warcraft 3 did have a proper programming language, but just you could make something and then you could play it, that kind of stuff. That's where it started.
Yeah, I feel like I also like those games. It's like masterpieces.
Yeah,
amazing.
Also, at one point, my father bought a very old computer, like a Windows 3.11 computer when Windows 98 was out, and there wasn't really much to do on that computer, and I found QBasic, which is a basic programming language, and started working in that. And it was definitely not a straightforward process because I didn't know anyone who programmed to help me. And this computer didn't have access to the internet. So I was just there like using the QBasic help file. I didn't know what a variable was. I figured out functions before I figured out variables somehow, which is ridiculous. I made a game which was just 24 subroutines where every subroutine said like, if they pressed left, call this subroutine. If they pressed right, call that one, and they would draw something on the screen. And eventually it would fail because the stack overflowed, which I assumed was because I drew too many circles. Like I had no idea what I was doing. But eventually figured it out, got better and better.
That's really cool.
Yeah.
So computer games was I guess one of the motivations to learn how it works. And then
I remember before I knew about arrays, just looking at like a game like Starcraft, and I'm like, how do they have like 1,000 of a unit? Like when I want to have 1,000 of something, I need 1,000 copies of the code. I don't know how they're doing it. And then, later you learn about these things and it stops becoming a mystery and it becomes just, well, of course that's how they do it. Like it becomes like, how was I ever confused about that in the first place? It's so obvious in hindsight.
One of these sort of underexplored opportunity was to how to gamify like ideas in things like quantum error correction. I think there are several fairly decent attempts to try to make it entertaining. But is there a way to make it both entertaining and scientifically insightful or valuable? Maybe the sort of fantasy I have is maybe a teenager somewhere playing this game is unknowingly solving some open problem in quantum error correction.
Yeah, there were some games that tried to do stuff like that with respect to optimization problems with surface codes. Like I said earlier, they were kind of invalidated by the style changing, where what the pipes meant became something different, and so you have that to worry about. I have thought before about like how would you make a game that intrinsically involved quantum mechanics, and it's surprisingly difficult because For example, take Tetris, the very simple game. You could imagine trying to do like a superposition of pieces or something, but then the pieces hit the bottom, and there's like no way to have them hit the bottom, as far as I know, that doesn't somehow count as a measurement. And this kind of problem seems ubiquitous in games. Like they're constantly doing things that if you try to imagine a quantum version of it, it would have measurements everywhere. So it just keep becoming classical. People have made attempts, like there's like quantum chess, and that's the main one that comes to mind, honestly.
What is it, like a superposition? Different.
Yeah, some of the moves were like put the piece in
Amplitudes.
superposition. Yeah.
Oh.
There was a game called Quantum Moves, which was doing like a wave function simulation, and you could like move around a barrier, and you're trying to get the amplitude from one place to another. So that avoids the measurement problem because you're just directly showing the amplitudes, you're not showing the outcomes. Yeah, in my case, when I say it's difficult, I was imagining like what would be a sort of game where you'd want a quantum computer to have to play it. And I've never been able to come up with anything good for that.
Do you want to show like a quick demo on the...
Yeah, I can show. Was there anything in particular that you wanted me to do in Crumble?
Maybe it's like if you have a surface code and you try to find a detector, is that easy to set up?
Sure. I mean, I can open one of the example circuits. There's various surface code circuits in here.
Okay.
So, right. A concept that Stim uses for error correction is this notion of a detector, which is just a set of measurements that has deterministic parity. And one of the tasks that you want to do in Crumble is find these things. So these deterministic parities always come from resets, forcing that to be the case. And so what this looks like is, you pick some reset and you say, I would like to track this forward. So I'm going to add basically the Z operator that this reset is preparing, and I can follow it forwards. In the timeline view, you can kind of see it moving around. And here I can go backwards and forwards between the layers to see it kind of spreading out. And in a surface code, after a few layers, we get to the measurement, and that reset operator has transformed into this 5-body operator, including the measurement. Now, if I don't include the measurement, basically saying instead of the qubits Z value, I would like to depend on the bit. If I go forwards, it's going to hit into this next reset, which is going to destroy the value, the qubit. And so it'll say, oh, you kind of, this is its way of saying you've lost track of it, that you've made a mistake.
So you're tracking the propagation of the error, essentially there? Or?
Yeah. Although in this case, it's not really an error. It's like knowledge. So I know the value of the qubit after this reset. It's +1 Z operator. And then after this C0, that knowledge has been transformed into, I know the ZZ operator across these 2 qubits. And then after these, it's become this 4-body Z operator and so forth. You can think of it as an error propagating forwards. You can think of it as this knowledge thing. The sort of intended interpretation for this task is as knowledge. But you'll do okay. Think of it as, oh, the error has crashed into a reset. Anyways, I can include this measurement, basically saying I'm going to depend on the bit instead of the qubit, and then I can make it to the next layer. And then now if I go forwards without including this reset, it's just going to stay where it is. So it's going to get pushed around a little bit, but end up back at these 4. And in order to get a detector, I need it to contract and disappear. But in order to make that happen, I can include other resets. So a bad choice would be this reset down here. I could include that. Maybe that'll make it contract. It does not. It just makes it bigger. But you can pick this reset here. You can include that one and say, the operator I'm tracking is that original thing I was tracking times this new value that I know it is +1. And then this compound thing will go forwards and will end up compressing down into the single measurement, which you can then include. So in a surface code, the rule is actually very simple. You just go to the middle of one of these squares, you include the resets of the measurements until it collapses back on itself. There are more complicated cases that come up, which is really where the tool becomes useful. For example, the paper that forced me to write this tool was doing this Y-basis reset. And there's this more complicated round here. So you can maybe see that what here on the left looks very different from what's here on the right. There's like yellow things and triangles and whatnot. Let's try to find a detector across that complicated thing. So first, I need to have one show up. So if I pick one in the very top right, it's sort of far away from the complications. I, again, do this rule of just keep including the things in the middle. And everything works fine, although there's this weird thing where it moves to the right because the circuit cycle is a little bit different here. But if I go right on this diagonal, which is really where all of the complicated stuff is happening, and I just try to include this one reset to get this four-body operator and then go forwards, I'm pretty sure this is going to fail horribly. Yeah, like really weird stuff happens.
So what is when you say reset? This is reset for what? For ancillars or for the
a reset gate replaces a qubit's value with a known value, typically 0 or plus. On physical hardware, it's almost always just the 0 state, like the ground state. In this simulator, I have X basis reset as well as Z basis reset, just for convenience.
Mm-hmm.
The way you would do an X basis reset on hardware typically is you do reset to 0 and then some pi over 2 pulse or some like a Hadamard gate.
So you want to, at some point, you feel like you'll maybe lost the physical qubit, you just want to switch it off? Or like when you say reset,
the reason that this qubit is being reset is we want to measure the stabilizer of the surface code.
Mm-hmm.
And we need somewhere to put that information.
Yep.
Ultimately, it's going to turn into some classical bit. But before that, it's going to be on some qubit that we're going to measure.
Mm-hmm.
This is the qubit that information is going to go onto. So in order to ensure that we have a clean place to put it, we reset it into the 0 state so that it's in a known state. And then we do these perturbations to it that if the stabilizer is in its +1 eigenstate, the qubit is unaffected. It stays in 0. If the stabilizer is in its -1 eigenstate, the qubit is flipped to the 1 state. So without the reset, you would need some other way of knowing the state of the qubit. For example, you did typically just measure this qubit before the reset.
Mm-hmm.
You could use that prior measurement value as the reference. And then instead of 0 versus 1 being +1 versus -1, it would be flipped versus not flipped.
It's like one of the basis states,
Yeah.
like collapsed one. I mean, 0, 1 essentially.
Yeah. Anyways, so currently this does something weird. I'm not going to try to describe it. Like one of the reasons is I have this tool, so I don't have to try to describe it. I can just like look at it and be like, that's not what's supposed to happen. Like before this, I would have like had pen and paper, just drawing this out by hand. Like, oh, it looks like it might be going horribly wrong, but I'm not going to know for another 5 minutes.
Yeah, what was the project or paper that forced you to do this?
It was to make an in-place Y-basis preparation for the surface code, which is actually what this example circuit is. It's from that paper.
So it's a logical Y-basis state. Okay.
So yeah, in the surface code, as with any other CSS code, it's very easy to prepare logical X and logical Z, to prepare 0 or to prepare plus. It's not always easy to prepare the Y-basis state, the ket 0 plus I times ket 1. And in the surface code, in order to do that, there was this proposal by Ben Brown, like in 2017, that you could do an S-gate by doing something he called like twist braiding. And this circuit is basically like a very optimized form of that, where there's a weird thing happening across the middle of the circuit here, which topologically I would describe as the twist zipping across it. I don't know how to break that down into details that people are going to understand.
Right.
I struggled with that in the paper as well. But that is where the idea came from, is the concept for this paper was maybe I can move the twist along the diagonal without ruining the code distance. And then I wouldn't need to grow the patch in order to make room for the twist to move and then shrink it again. And then it would all be in place instead of needing a lot of space.
And how's that connected to finding detectors?
Well, this is a fault-tolerant circuit, and so it kind of has to be filled with detectors. It has to be filled with little things that you're checking constantly in order to notice that things are going wrong. So that's finding detectors is a subtask of I want to make any logical gate.
Right. So it was the need to figure out how to in place prepare this logical Y-basis state that drove the need to build a tool for detectors.
Yeah. And like these patterns of gates, like, oh, I do this. This is an X controlled Y gate. Like every other one, but I don't do it here. Like little exceptions like that was what was killing me. And the ability to just focus on one part of it and say, okay, how does the Pauli move around here? Okay, maybe I can change this gate to fix that, and end up make gradual progress towards correctness instead of having to get all correct at the same time. That's what this tool allowed.
And I see that this probably you can do any stabilizer code defined on 2D geometry.
Yeah, it does like 2D codes more than 3D ones because it fits better on a screen. It's definitely one of the downsides from the perspective of people who want to work on 3D codes, though.
Or any sort of codes with non-local connections.
Yeah.
Where do you see this tool?
It can do non-local connections. Like you can do gates that go long ways.
Okay.
It's just going to be a bit more of a mess. Like they'll all be crossing each other, and it'll be harder to see what's going on.
Right.
This is a generic problem with making these non-local codes. Is they're just harder to visualize.
And have you seen people using this for LDPC code and these more recent code design?
I'm not aware of any instances of that happening. It's possible that someone has.
And the main appeal is that it visualizes the calculation and it saves sort of the manual effort to sort of keep track of everything.
Yeah, and that makes a big difference. If I was doing things with pen and paper, I would never say, oh, what if I just delete this one gate? Maybe it works then. Because that's going to take me 5 minutes to try. But here, like I can just be like looking at this box here, and it has this magenta outline around it, which indicates that something has hit a reset that it shouldn't have, for example. And I can just go to a gate and I can hit delete and just see, like, did the magenta box go away? And so maybe this one gate fixes it. You can just try. And it's not necessarily a great strategy to just throw random things at it like that, but sometimes that works. Like sometimes there's just some little mistake, you make some tweak in it, and it still functions. It can also be really useful where you have a functioning circuit and maybe you suspect a certain gate isn't actually doing anything interesting or useful. There's been a surprising number of times where I've made a circuit and just deleted a gate out of the middle and seen like, oh, the output didn't break. Like, why didn't the output break? And then you find out something interesting from that, and maybe it turns into an element of a paper later.
Mm-hmm. So do you have a set of other favorite tools you like to use when working with logical qubits in addition to what you build?
With logical qubits, I use SketchUp a lot for surface code things. So this is just a 3D modeling tool. We make these, they look like pipe diagrams. Like they have junctions and pipes between them. The pipes have two colors. The colors represent the X and the Z basis. And there are certain rules for working with these diagrams that mostly I just do by hand in the 3D modeling software and hopefully don't make a mistake while I'm doing it. There are efforts to try to automate this process more. It's kind of tricky because we keep coming up with different ways of embedding qubits into these systems. So back in 2012, for example, the way that you put a qubit into a surface code was not this way that's sort of drawn here where you have a box and inside of it is the logical qubit. They were instead on you can think of it as like an infinite plane of surface code. There's a very large ocean of surface code, and they would punch holes into it. And the qubits would be wrapped, in a sense, around the holes and between the holes instead of being in their own little boxes. In the type of diagram that you draw for that, the pipes only have one color instead of two colors, and they don't connect to each other. They wrap around each other. And there were people who made tools and I think even like games where you could try to optimize these structures, but they ended up being obsoleted by this other way of embedding the qubits. And so in a sense, all that work was lost because it was spent on something that got replaced. And this is maybe part and parcel with being in a research field where we're constantly improving things. Anything that we make is very likely going to be replaced in 5 years because it's a continuously improving process. But the amount of effort to make a 3D tool where you can edit things is substantially higher. And so it's a lot of work, and it can take long enough that maybe by the time you're done, it becomes obsolete. So I I've tried to like start these 3D tools before, and then it gets like obsoleted before I finished, and it sort of turned me off the idea of that, at least for now.
Interesting. Yeah, that's what quite impressive. Like, let's say, looking on the right side, those like the strings circuits, and then on the left side, how compact and self-contained and informative could it be done, visualized. I think that's definitely like driving the field forward. I think with Austin, what we're looking at this optimization, the TQC,
the ZX diagram,
the topological.
There actually is
optimizing the quantum circuits.
There is a tool on the website that's not listed, which is for working with ZX diagrams. I don't really recommend that people use it. It does exist. It's called Zigzag. And you can make little ZX diagrams. And the tool is very easy to crash, which is why I'm not really recommending that people use it. But yeah, it'll compute, what operator does this correspond to? It'll compute the stabilizers. And let's just crash it. There we go.
Crash test.
Yeah, I also use the ZX calculus a lot. I like it as a language for quantum processes because it's more abstract than circuits, but it's very flexible. And I find the extra flexibility allows me to encode physical assumptions that I want in a way that can be difficult with the circuits. I don't have a great example of this. Well, there's like a one-to-one correspondence between these diagrams and the lattice surgery diagrams. So we make the 3D diagrams. And those 3D diagrams, when you try to express them as circuits, they end up very messy. They have all of, I have many circuit diagrams in my papers that I have to like fill with annotations where I'm saying like, this is supposed to be this measurement. I know it doesn't look like that, but that's what it would be in lattice surgery. And as the ZX graph, it just looks the same.
I assume it must be like for, lead code for quantum computing where you do it by hand, derive, draw the circuits, draw the logical qubit states and the stabilizers.
Yeah, it's kind of ironic. Most of the I write a lot of tools, but almost none of them have to do with automatically generating a circuit or automatically compiling it. It's almost always like a tool to help with manually making a circuit. And it's kind of the same reason that I was discussing before. It's because we keep making improvements and we keep invalidating the assumptions that these tools are based on. And since all of the good work, the work that I'm happy with that I'm the proudest of has to do with like, oh, this paper said they had the optimal construction, but they assumed this thing that they didn't realize they were assuming. And if you take that assumption away, all of a sudden it can get much smaller. And if you're using automated tools to generate the circuits, they're going to embed those assumptions in a way that's very difficult to remove. And so in all the tools that I make, I try to avoid that. And one of the easiest ways to avoid that is to just ask the user to enter the whole circuit. And just have a whole family of things that you can simulate and let them explore. That's a lot harder to get started in, but it doesn't lock you in.
Yeah, let's talk about Quirk.
Yeah, what's the Quirk?
I remember playing around with it some time ago. It was this visual tool for building and running simple circuits. I'd be curious to see like what will be its limit. Like what are the kind of circuits that will kind of stretch its limit?
Well, an obvious limit is that it has at most 16 qubits, so you can't go further than.
So that's hardwired.
Yeah, but one of the reasons for that, if I can zoom this out.
How old is this tool?
I think 2016, so about 10 years.
That time 16 qubits was good enough.
It's really more to do with I want to be updating live. I want to hit that 0.1 second thing. So, I mean, I can give a very clear example of this.
So you don't like to drink coffee?
Yeah. Just put so these what's happening right here on the screen is it's simulating the 16 qubit circuit, and every time it's drawing a frame, it's picking a different value of t. And it's showing the output state here. And I mean, this just kind of looks cool. I don't know how useful it is, but the fact that it can do this is why I stopped at 16. If I'd gone up to 20, this would be very slow. It would be a frame every 2 seconds or something.
Oh, is every pixel a matrix element?
It's a state vector. So every pixel is one of the basis states, and it's showing the amplitude. It's drawing a little line that's oriented depending on the direction. The length of the line is the logarithm of the amplitude plus some offset. And so, I mean, I can reduce the size so it's a little more obvious.
Oh, okay.
Let me just actually make it really
And
small.
what is happening there? What kind of gates are you applying?
It was a QFT and some
QFT,
X basis rotations.
Uh-huh.
But here I can make a bell pair.
Can you show here some of the period of the modular exponentiation elements of like finding the period of the function?
Yeah, one of the example circuits is where is it? Shor period finding. So zoom out a little. This is a little mini version of Shor's algorithm with a very small case. So you prepare a uniform superposition in one of the registers. Based on that value, you multiply, you do a modular exponentiation into the other register. Then you Fourier transform the input, and you get these frequency peaks. And in this case, because I'm hoping I'm not getting this wrong, because the period is 5, you're getting 5 peaks. One of them is sort of hidden here at the top. You only really see 4 easily here. And then there would be some post-processing where you would get a sample of from this, because you don't actually get to see this distribution when you run the algorithm. You get some sample, and it's more likely to be near one of these peaks. And you would have to do some post-processing to figure out, like, oh, this was a peak that was near one of the multiples of 1/5, as opposed to 1/7 or something. Yeah, so that's a little example of period finding.
So it shows the amplitude as a function of
this here is showing the for each potential output, what is the probability of sampling that output if you were to measure right now. And then this here is showing the actual state vector. So you can maybe kind of tell that there are these bands that are equally spaced. It's maybe a little confusing because it's including this bottom register. If I just add this display here, it's not going to show the phases. Well, it's sort of maybe hard for you to see. I can zoom in. It's showing them as empty circles instead of circles with a line because it doesn't know the phase because it's entangled with the other qubits.
Wow, that's amazing. I think it should be used for this kind of explanation of the Shor's algorithm. And then
there are various university professors who've contacted me and said they've used it in their courses to show people, because it's so easy to see the intermediate states.
Yeah, it gives like some intuition.
Yeah.
Like more like a high level view of what's happening. And
yeah.
Was this also from a project where you were trying to gain some insights about a circuit? And
this was when I was like learning quantum computing. I was using another simulator, I think by Davey Whipple or something, and it wasn't slow exactly. It's just you had to hit a button for it to run the simulation and show you the output. And the output was written as like text. It's like the kets and their associated amplitudes. And that's just it's kind of slow to interpret.
Yeah.
Where here, I mean, like as I'm dragging it around, it's showing the output. So there's much less delay. And you can, go out of your way to try to make it, if you're testing something, that everything will look quiet. No dark colors if it's going well. And if you make some mistake, it kind of lights up. And then you can very quickly edit a circuit and you'll have some little thing that's telling you made a mistake. I can maybe do a very simple example of that. Suppose I want to implement a Toffoli gate. I can use a trick called the state channel duality. Just make a bunch of entangled qubits and apply the Toffoli gate to it. And then undo it. Oops. Undo the preparation of the bell pairs. So I'm just doing something and then undoing it. But suppose I want to find some implementation of the Toffoli and I'm making, and I make some mistake while I'm doing it, like I accidentally have an X gate. Then I see something lights up over here. And so as I decompose it, I can catch mistakes. So I can try to do a textbook decomposition of the Toffoli. which I have done so many times that I know off by heart.
It's like a typical day of Craig.
T and this.
Back in 2016.
And that is like that, and like
When
this.
NISQ era quantum computers.
So, okay, I just spit out a whole bunch of gates. It's off, so I know it's correct. If I made a mistake, for example, if I got this T dagger as a T, I would have something here telling me it's wrong. So a lot of the circuit stuff that I was doing, I'd like set up this kind of test harness and then just do whatever. And so this, again, makes it very easy to test things. Like I can easily check, do I need this gate? If I delete this gate, does it stop working? Yes, it stops working.
Mm-hmm.
And behind the scene, does it run a full state vector simulation?
Yeah, this is doing full state vector sim.
That's really cool.
Yeah.
I didn't know about this tool. I wish I did. So I feel like one of the probably like pressing things on the society is the like Shor's algorithm and breaking RSA, elliptic curve things. So you have several works on that, like optimizing the resources needed to achieve those goals. Maybe if we could kind of go into the details of how do you, there was like estimates of the earlier one that you need like something like 20 million qubits, physical qubits, and then 8 hours to do that. And then how do you get this estimates?
So I do work on the algorithm itself. So just try to come up with a good arrangement of additions and lookups and so forth to implement the difficult bit, which for factoring is the modular exponentiation. And then I try to translate those things into actual surface code constructions and actual layouts. So in a sense, these estimates are kind of upper bounds. Like the surface code is sort of one of the most vanilla codes. It's, if anything is going to work, that's going to work. Modular having enough qubits. And so the kind of goal of those papers was the estimates that people had were too high, and people in the classical world are presumably basing when are they going to transition to post-quantum cryptography that's not vulnerable to quantum computers on how expensive do these things look. And it's very bad if there's a factor of 100 between what the cost appears to be and what it actually is. And these situations do come up where advancements are made and the cost goes down. And so you want to tell people so that they have an informed decision-making process. So in the 2019 paper, I showed that you could factor with 20 million physical qubits with surface codes, where the previous estimate was somewhere around 1 billion. It depends exactly which previous estimate you pick.
How did they overshoot that far?
I mean, just the techniques got better.
What was the previous result? Which year was that?
The clearest, like most direct comparison is one from 2012, which was a paper by Austin Fowler, the surface code architecture paper. That's very well known within the field. It includes an estimate of the cost of factoring. So one of the reasons that the cost was higher is their T-gates were more expensive. They were using less efficient magic state factories. They were using braiding style surface codes instead of lattice surgery style surface codes. Another reason is they didn't know about certain arithmetic optimizations, such as we call windowing. So something that you do in Shor's algorithm is you keep doing, do a multiplication with a classical input conditioned on a qubit, and then do another one, then do another one, then do another one. If you have 5 of these in a row, you can think of this as a combined problem, which is I want to look up out of 32 possibilities, what should I multiply by? And then if you do it that way, you only have 1 multiplication to do instead of 5. So that generic technique we call windowing, and they didn't have that. And that saves you like easily a factor of 5. You have to be a little careful because as the window gets bigger, the size of the table blows up exponentially. So you can't use like a 100 qubit window, but a 5 qubit window is completely doable. And I think in my estimate, I used like 10. So it's getting a little bit expensive, but it's saving more than it's costing. So that reduced the number of gates pretty substantially. When you have fewer gates, your code distance can go down. That can save a little bit of space. But I do think the most significant changes were actually in the style of fault tolerance, using lattice surgery style qubits instead of braiding style qubits and having better T-state factories.
One thing that would be interesting to get your perspective on is how sensitive these resource estimation numbers are to like these detailed incremental improvements at different layers. Like you, for instance, if you have improved implementation on the arithmetics or better method for arithmetics or better error correcting code, like it seems like they all kind of stack up and then they can make a big difference.
That's right. I think at this point we're probably pretty good on the algorithmic side, like the series of operations that we want to do. So I put out a paper last year in 2025 where this estimate was reduced from 20 million to 1 million. And that was mainly due to Chevignard et al. Finding this way of doing an approximate modular exponentiation without using a lot of workspace. I can go into more detail there, but that was like the most important.
Is this the yoked?
No.
No, that's a different one.
No. This was, I forget what they called it. It's just doing residue arithmetic, where you, instead of doing arithmetic modulo the number you're supposed to, you do it modulo all of these small prime numbers and use that combined information to rebuild the result. And because each individual thing you're doing is modulo some small prime, it doesn't take a lot of space. And so the whole trick is to do the reconstruction in a way that doesn't ever fully create the big number that you're tracking and only makes a small section of it. So in my 2019 estimate, I used 3 times n qubits. So n qubits for just like holding the state, like the current result of all the multiplications. N qubits just as workspace for the multiplication, and n qubits for the lookup to do the windowed arithmetic. With the Chevignard result, they used n over 2 qubits plus various small registers. So it ends up being something like 2/3 times n for n equals 2048. And so that's a big reduction going from 3 times n to 2/3 times n. And then there was also the stuff with denser storage using what we called yoke surface codes. And we, again, had better T-state preparation. So at that point, we knew about magic state cultivation. So the storage got smaller, the computation got smaller, the magic state preparation got smaller, and it all combined together into 20 times less space. It's hard to imagine the algorithm improving more at this point. This is maybe this will look foolish in hindsight, but I can't imagine any way that you can get below n over 2 qubits for the state, because the period that you're trying to figure out is of order 2 to the n over 2. So it seems like you need it. On the other hand, 3 years ago, I would have said the same thing about n qubits. Like when you're doing arithmetic with an n-bit number, like you need to store it.
All right.
It's obvious that it can't get too low. Like if it was log of n qubits instead of O of n qubits, then that would correspond to an efficient classical algorithm via quantum simulation. So I think all of the advancement that could still potentially happen is on the fault tolerance side, lowering the cost of the fault tolerance.
Also, there is another, I think, bottleneck is related to measurements.
What do you mean?
And making the decisions on how do you want to correct the errors.
Oh, yeah. During the execution of the algorithm, there's many cases, where there's a certain measurement that determines whether or not a certain gate has to occur. And there's long chains of these.
T-gates, especially, probably the best example.
Yeah, when you prepare a T-state and then perform a gate teleportation with it to perform a T-gate, there's an S correction that you have to do, or some other Clifford correction. And there are many T-gates in this algorithm, or many Toffoli gates, like almost 10 billion. And mostly they're done one after the other, at least the way that I laid it out, because there are, for example, I use a ripple carry adder, which has linear depth, instead of a carry look ahead adder, which has logarithmic depth. The reason being, if you have a massively parallel adder, you have to feed it enough magic states to actually run it. And the number of factories that I have is like 6. And they're not going to be able to feed the carry look ahead adder. And so it would just bottleneck and end up running serially. And it needs more Toffolies than the ripple carry adder. So you just lose. So yeah, that has linear depth. And there's all these chains of, I do a non-Clifford gate by gate teleportation. I have to do a Clifford correction. Then I can do the next one. We call this the reaction depth of the circuit. My talk at March meeting this year was about me not having understood the reaction depth 3 months ago. We found a bunch of subtleties in it. But it sets a limit on how fast you can run at least a given form of a circuit. The reaction depth times your reaction time, your ability to decode and do the next measurement and do that cycle, is a minimum on how fast you can run the algorithm, at least under this style of execution that we use.
Yeah.
Yeah.
I think one thing that's very useful to highlight, like in the middle of this, is that I think maybe part of this is your paper directly says it's X number of qubits and X amount of time.
Yeah.
But in reality, it's a whole frontier of trade-off.
That's right.
Like if you want to go faster, you can throw more qubits at it. I think it's useful to, because people like to quote that particular title, but in reality,
there's so many details underneath.
Yeah, no, I do that
What you can
intentionally.
play
I simplify it into a single point to make it simpler for people to talk about.
Right.
In the actual paper, you'll find these like frontiers, or if you have a computer that's twice the size, essentially you kind of get to pick, for each qubit, is this qubit doing compute or is it doing storage? And if you have a computer of twice the size, but the problem is the same size, the amount of storage you need hasn't increased. And the storage is something like 2/3 of the space. And so the remaining 1/3, which was used for compute, all of the doubling is just adding to that. So you went from 1/3 compute to 4/3 compute. And so there's a sense in which doubling the size of the machine, you expect it to run 4 times faster. I didn't try to optimize for what's called minimum volume, like minimum qubits times time. I preferred to have fewer qubits at the cost of more time. Not to an extreme level, but I absolutely was willing to take a factor of 4 loss on time for a factor of 2 savings in qubits.
Makes sense. You're probably
Yeah.
gonna take a longer time to build that number of qubits than just to wait.
Yeah, you have to be a little
demonstrate.
careful. If your time estimates start being in years, then I don't believe them anymore, because that's enough time that someone could build a bigger machine.
Mm-hmm.
And I'm trying to warn people about when the first thing might happen. And so if you say, this will take 20 years to run, but then the year later they build a machine that's twice as big and the 20 years turns into 6 months, you sort of failed at the goal.
Yeah.
And I think that was the interesting idea of on the storage space, the yoked surface codes.
So one of the ideas that we had for improving the density of surface codes, like one of the worst properties of surface codes is their density. Like a typical thing you might imagine is 1,000 physical qubits for every logical qubit in a surface code. And that's a big overhead that turns 1,000 qubit algorithm into a 1,000,000 qubit algorithm. And so we're always interested in finding ways to improve this. And I work specifically on a superconducting team where we expect a planar layout, and this heavily limits our options. Like we can't use any crazy non-local connections, or if we want to, we have to then build that. Like it's an extra requirement for the hardware team to meet. But we do find things that can improve the size even despite those restrictions. And yoke surface codes are an example of that. So the idea is essentially what would be called concatenation. We just take a very, very simple code, which is the 2 stabilizer code. Like you have one all X check and one all Z check. and you concatenate that over the surface code. So you have your surface code qubits, you store them a bit smaller than you would otherwise, but every once in a while you do logical X checks on all of them and logical Z checks on all of them. If these checks fail, you know something has gone wrong. You don't yet know what went wrong, but one of the benefits of the surface code is when something is going wrong, it tends to leave signs. Like you can compute like a suspicion score.
Right.
And you see something went wrong, you go back over the records, find the most suspicious thing, you guess that's probably where it went wrong, and you apply the correction based on that. And this ends up working pretty well. It reduces the physical qubits per logical qubit by a factor of 2 to 3. It's a little bit more inconvenient to compute on qubits that are stored in this way. And so we separate the algorithm into like the storage area and the compute area, and we kind of unyoke as they come out of the storage and re-yoke as they go into the storage.
How do you implement that?
So the qubits in the yoked storage will still correspond to some, like the logical qubit will correspond to some Pauli product of the surface code patches. So the X operator of the logical qubit within the yoked code will correspond to like X times X of the underlying surface code patches. And lattice surgery makes it very easy to access Pauli product operators. So what it would look like in one of these pipe diagrams is you just have some pipe that was reaching into the area and it would touch 2 places instead of 1 place. You have to be a little bit careful here, like the pipe itself has to be big enough that you're not introducing what are called hook errors, where you would simultaneously cause those 2 things you touched to fail. So there's details, but that's roughly what it looks like. It just looks like normal lattice surgery, except you're touching a few more things.
So now all this yoke surface codes plus, let's say if we can wait longer, like all of it combined, what's the bottom line at the moment in terms of resources needed to...
In that paper, I estimated 1 million.
1 million? That's still...
So that's like the vanilla estimate. That's using the simplest code with the easiest requirements and assuming very plausible gate error rates. Like I assume a gate error rate of 0.1%. There are already teams, like ion trap teams, that have gate error rates lower than that. And like the superconducting teams are all approaching that. And there's no particular reason to expect it to suddenly stop when they hit 0.1%. They might just go by. So that gate error rate getting a little better in practice was one way the estimate might get lower. Another assumption that I make is that this planarity constraint. So you have a square grid, qubits talk to their nearest neighbors. If you have an architecture where that's not a constraint, like a neutral atom machine, you may have better codes, and so you may be able to get denser. One way that assumption is potentially optimistic instead of pessimistic is probably you're not going to build like just a big square grid as one physical object. There's going to be divisions within it, like modules, and there'll be a little bit noisier across those divisions. That's one reason the estimate could go up. But mostly I expect it to go down.
I see.
Yeah.
I don't know, any bright sides, like from LDPC side, try to encode a smaller number of, maybe like same number of physical qubits, but into larger number of logical qubits. Does it
So
help to shape the
So numbers? I don't know a lot about what people call good LDPC codes, partially because of this planarity constraint. It kind of keeps me focused, let's say, or maybe keeps me distracted, depending on your preferences. There is currently a big gap in the literature between the types of codes that people propose kind of in the abstract without really thinking about how it would run on a machine, or like in this code capacity model instead of a circuit noise model, and the things that could plausibly run on machines. And people are definitely working to try to close that gap. So if they did, then the number of qubits could drop a lot. Like there's a paper that came out claiming 100,000 instead of 1 million, based on this kind of changes to the assumptions.
Yeah, but then the complexity of implementing.
Yeah, they kind of the way they do the estimates is they don't really commit to superconducting numbers or to neutral atom numbers. and they sometimes kind of take the better of both worlds, which doesn't really make sense. But the broader point of if you're willing to make these stricter assumptions, the cost will come down is true.
Yeah. At the algorithm level, I think you mentioned this insight about using smaller primes, and this reminded me of Regev's factoring algorithm that also leveraged a similar sort of insights. That has
he uses small primes very differently, but it is also small primes.
Yeah, and the paper suggests better asymptotic scaling, but do you think there's a chance that the prefactor may be actually not so bad that it actually makes a difference?
Does that paper actually suggest better asymptotic scaling once you account for the increased number of shots?
It was
it's like 2.5n Toffolies instead of n to the 2.5 Toffolies instead of n cubed, I think. I think I'm misremembering this actually, but to my understanding, the total amount of work you have to do when you're using Regev's algorithm is not asymptotically lower. It's the per shot work that's lower. I hope I'm not wrong about that. But that's not really my issue with that algorithm. The thing that makes me not pick it when I'm doing estimates is that it needs more space. So the original algorithm, I think, needed like n log n space instead of O of n space. And that's been improved since then by Vinod. I'm sorry, I can't remember the people's names. They had something like, you need like 5 times n or 10 times n, something like that. So their competition is n divided by 2 plus a little bit. So maybe they can bring it down more and more and more. Given the structure of that algorithm, I'd be very surprised if they could get it as low. And since, at least for the first vulnerabilities that quantum computers might exploit, it's probably all going to be about qubit count. I don't think that it'll matter for that case. Maybe it ends up mattering once computers increase in size later and you can start fitting more ambitious things.
Right.
Yeah.
And it's the prefactor in the number of qubits.
Yeah, and then the other thing is the estimate on the asymptotics, like on the number of gates. Is it mostly done based on modular exponentiation, like this kind of breaking down into
for Regev or
for either Shor's or Regev?
It almost always comes down to the modular exponentiation. I'm not aware of any case where it doesn't.
So that's what you just need, Toffoli gates, and which can why are we not targeting directly Toffoli gates, but more like trying to implement the T gates?
In my estimates, I do directly target the Toffoli gate. So, for example, in this 2025 paper, the magic state chain is do magic state cultivation to prepare T states with an error somewhere around 1e-6 to 1e-7, and then use the 8T to 1 CCZ distillation factory that Cody Jones found in order to produce a CCZ state, which can then be directly used to do a Toffoli. That factory has quadratic suppression, so the error rate of those states can easily be 1e-12, which is more than sufficient if you're going to do 1 billion to 10 billion of these.
I see. So it's like another part of CCZs. Yeah, maybe like also speaking about the T factories and like, I mean, one of those ideas of magic state cultivation. What do you see like the next paths in terms of optimizing on cutting on the T gates, or maybe producing them in a better way?
I don't know. There was a talk at March meeting yesterday in one of the sessions where someone claimed that they could make 3 CCZ states at 10 times less cost than the cultivation T state. But I don't know if I trust it yet. It looks very promising. They haven't yet managed to get... it's still ending in small code distance. It's still ending where they're doing error detection. And an important part of this process is you have to transition to error correction, which involves increasing the code distance. So in a sense, the idea is not done. but they have apparently done circuit noise simulations, and
With Stim?
I don't
something
know if
else?
they use Stim because magic states are non-Clifford operations.
I see,
Stim can
makes
be
sense,
limiting. I think they might have done a proxy where they use Stim, but instead of the CCZ gate, they did like CZ gates or something. Like you can do these little kinds of cheats to get a sense of where the error might be, but you won't really know for sure. You'll probably be off by a factor of 2, for example, until you do the non-Clifford simulation. But yeah, that's something that I'm currently excited to look into once I get back into Santa Barbara.
Also, another thought is about, I feel like what the field is missing, like the decoding.
Yeah, so especially for these more complicated codes, like the surface code is a very easy decoding story.
I see.
It was you use Blossom or you use Union Find. These are very fast and they're pretty accurate. They're not perfect, but they're quite good. For more complex codes, people use belief propagation followed by something, and this, depending on what they follow with it can be very slow or it could not be accurate enough. This is probably one of the major obstacles to people finding good LDPC codes, is making sure that you can decode it as fast as the machine is going to run. For superconducting machines, this is particularly a problem because our rounds take around a microsecond. And so your decoder had better be able to process one round of information per microsecond. You may have multiple parallel instances.
But for surface codes, you're saying this is solved problem even for
I don't know
like
if
a larger scale?
I wouldn't say it's
distance?
solved, like that the artifacts that do it exist. It's just clear that they could. Like, someone could make an ASIC or they could program an FPGA to do this. There are various claims of various levels of progress on this problem.
Maybe some machine learning, like
Oh yeah,
training a
yeah.
model,
People look into
inference.
machine learning stuff. Yeah. There was a very recent paper or preprint that I found very interesting, which claims they have a proof that color code decoding is NP complete, that you can embed 3 SAT problems into it. Now, those aren't going to come up in typical decoding problems, but it was unknown for a long time if this problem was NP complete. Like, no one could find a fast decoder for it, and no one could show that it was hard. So that's a little bit of recent progress, maybe in the negative direction with respect to, for sure, being able to do it efficiently. Yeah, I think the decoding problem is going to get worse before it gets better. I think it's a major bottleneck right now. If someone could find a faster decoder or that applied more generally, I think that would be an example of a very impactful paper.
And typically for decoding, how many errors like being marked in the logical qubit? I mean, the physical. Like, you basically understand, you try to identify which of the physical qubit and what error was.
Are you referring to the detection fraction?
Maybe like both. I mean, detection and then finding out what, like from the syndromes, finding out what needs to be done to the surface code, or in general any code. How it needs to be changed to take into account the error.
I mean, typically you don't have to do a change on the quantum computer for the decoding. You just have to know when a measurement occurs, is it flipped or not?
Like doing some back calculation later. Yeah,
this is actually a very surprising property. It's not true of all codes. It's true of, I think, all stabilizer codes. Because an X gate or a Z gate or a Pali gate can be pushed through a stabilizer circuit while only becoming Pali gates. It'll eventually, if you propagate it forward far enough, either flip or not flip every measurement and do nothing else. And so if you do that process in the classical control system, you don't have to do the Pali corrections on the quantum computer. And this is great because it means that the quantum computer doesn't usually have to wait for the decoder to figure out what the correction is before continuing. Codes with that property, we call they need just-in-time decoding. And that's I consider that to be a major problem with a code, or a major technical obstacle that is going to force your decoding to be much, much, much harder because you have a very hard deadline that you have to meet.
is there like a certain stage where you still need to fix the errors?
Yeah.
Because otherwise they'll be like spreading, accumulating, and it
Yeah, an example
causes
of this.
exploding.
Yeah, typically codes that have, well, I hope I'm not wrong about this, but typically codes that have like a transversal T-gate, they need to have their stabilizers in specific eigenstates before you do the transversal T-gate. So like they should all be in the +1 eigenstate, for example. And if they're not, it'll just do really bad things to the state. Like you'll lose the code. So you need to actively keep those stabilizers in the +1 eigenstate. Whereas in a surface code, for example, or most other stabilizer codes, or at least if you're not doing a T-gate, you just let them drift however you want. You just have to keep track of them. You have to notice when they flip. But if it's currently -1 and staying -1, or if it's currently +1 or staying +1, those are both equally good situations. In fact, there are potentially some advantages to having a few -1s around, because if you have some sort of global noise mechanism that causes all the qubits to rotate by a small amount, but in the same direction, it will kind of build constructively on itself if everything's in the +1 eigenstate. Whereas if you kind of randomize them, then it becomes more incoherent.
So are we? I mean, in general, I can see there's like the main trend is now this kind of digital quantum computation. Do we? Are there other avenues which are like completely different from this trend? We kind of considered for the use case for a quantum computer.
There's a very common thing that people suggest for early fault tolerance, where you make the Cliffords properly fault tolerant, but for rotations, you just inject a specific state, for it. So that will be noisy. And you'll be limited by how many of these you can do, but you're not limited by the Cliffords. That's an example where it's not fully digital because the injected states are kind of analog. They have a continuous angle. But other than that, I'm sort of a big fan of fault tolerance as the way to go. Maybe not surprising given the sorts of papers that I put out. Current machines have error rates 1 in 1,000, 1 in 10,000 per gate. And this kind of means that whatever algorithm you run, you don't want it to have more than 10,000 gates. Like if you put out an experiment today and you manage to do 10,000 gates and get a decent end-to-end fidelity, that's considered extremely impressive. Whereas with fault tolerance, like the algorithms we want to run have billions of gates. And it's just not really plausible to reach that without some kind of error correction. It would be amazing. Like classically, this did happen. Like classically, they were originally going to do computation electronically with vacuum tubes, and they would burn out and they would fail in other ways. And so they thought they would have to do error correction while they were running. And then the transistor was discovered, and it's just ridiculously reliable. It's like you try to do back of the envelope numbers of how reliable a transistor flipping is, and you get insane things like 10 to the -20 error rates, which is not so low that we don't see it happening.
Still use parity checks.
No, they're like papers in like cryptographers publish papers like, oh, I registered domain names that were 1 bit flip off from the real domain name, so it's unlikely to be a keyboard typo by the person, but like a computer mistake. And they get hits on those domain names. So we know that there's finite failure rates in classical computers that we aren't bothering to fix. They're kind of good enough. They're not perfect. But yeah, the transistor is amazing in terms of its reliability. It would be great if we got something like that for quantum computers. I don't know what it would possibly be. Yeah, it would be great if all the work that I did became unnecessary and it just became easy.
Yeah, I think this is one of the mind-blowing paradigms of like classical computing, that p-n junction somehow is so robust. While in quantum computing, we're trying to, it's quite fragile.
Yeah.
And we're trying to build something of very fragile.
It's wildly different. Like people run like some supercomputer computation with trillions and trillions of operations. And how do they check it? Well, they'll run it twice and hash the output and check that the hashes are the same.
Yeah.
Like this is checking like 200 bits for trillions of operations. Whereas in quantum codes, we're like, okay, for every operation, we're going to check thousands of bits. So yeah, it's a massive difference.
Yeah, and what does that mean for the software stack? Because it seems that there's a lot of evolution in hardware and also in how we think about error correction, all the way to how we think about implementing algorithms and also the algorithms themselves. So if there's a way to sort of integrate them together, like integrating the results together, where, for instance, someone comes up with a novel implementation of an algorithm, we can directly plug that in to this hypothetical stack and then get some results out. It seems like we are very far away from this kind of modularity where we can do that. It seems like a lot of this depends on expertise.
Part of the problem is that different architectures have different things that are expensive. So as an example, in a surface code architecture, doing a multi-target controlled NOT gate. So you have one control, and if it's on, you want to flip many qubits, is notably less expensive than doing the same number of controlled NOT gates separately. Because in lattice surgery, it's somewhat inexpensive to access these big Pauli product operators. And so if someone gives you a circuit, you kind of want them to have expressed it in the way that makes it cheap to run. And if they haven't expressed it that way, you have to do a conversion. And when you build these big stacks of like this compiles into that and that compiles into the next thing, you can easily get into this failure mode where you kind of convert it this way for that layer and then convert it back for the next one and like lose something in the process. So something I worry about a lot when we're going to eventually make these stacks is like, what actually should the input format be? Because I don't want to have the user specify something that you then have to figure out what they intended when they could have just told you directly.
Like, what would be an example of this?
For example, someone who likes the ZX calculus specifies their algorithm in the ZX calculus. They run it through a tool that converts it into a circuit. And then they run it through a tool that converts the circuit into a surface code computation. And inside that tool, what it does is it converts it into a ZX graph.
Right.
So that conversion from ZX graph to circuit to ZX graph is almost definitely going to cause an inflation in the number of operations. And it's very easy for these sorts of things to appear when you have a whole bunch of people working on different parts of it. I don't think we've actually suffered from this yet, but I kind of worry about it as a future problem.
Right. It's like you could say premature modularity or like premature abstraction.
Yeah. There is also this issue of anytime you put in an abstraction boundary, you are going to pay a cost because it's going to be not possible to express certain things that would be more efficient because those things have to cross the abstraction boundary. And we will have to put abstraction boundaries in. It's not plausible that someone thinking about chemistry algorithm is also going to be thinking about exactly what the quantum error correction looks like. But if we manage to find good abstraction boundaries, hopefully there won't be too much loss along the way.
Yeah. And then the other extreme would be if I was trying to, say, implement an adder circuit, and I think very deeply about, say, LDPC code, and is there a way to somehow implement this adder in a very slick way in an LDPC code that is faster than any other way?
Yeah. You could plausibly imagine some kind of code where through some symmetry that it had, that addition was somehow easy. I don't know of anyone claiming such a code, but you could definitely imagine certain operations are cheaper. So for example, people find codes that have certain like automorphisms that you just swap a few qubits and this is equivalent to having done a logical CNOT. And so in a code like that, you kind of stop caring about the CNOT gates and you care about some other gate. Another example would be in the surface code on a planar chip. When we do single qubit gates, we do them, it takes D rounds. If we used a color code instead, it would take 1 round or even less than 1 round. And so the relative cost of the single qubit gate versus 2 qubit gates is very different. And you can express circuits in ways that use more single qubit gates or more 2 qubit gates with very simple rewrites. And, do you ask the user to do the correct thing? Do you convert for them?
I think all of this sort of underlies the sort of unspoken complexity behind questions as simple as, when are we gonna break RSA 2048? Like, I feel like the deeper we look into this, right, the more we see that, someday someone can come up with an idea that straddles these layers of abstraction, and that totally changes the way we frame the question.
One of the major advantages that someone who's actually built such a machine is trying to use it is they know exactly what the machine is. They don't have to say, what if it was this, what if it was that, and think about all those different scenarios. They have one thing to think about. And also they can just try it. So they don't have to make a proof that something will work. They can just see, does this work?
So it's like a lower level kind of programming, or trying to get closer to the hardware, take into account its particularities.
Yeah, even at the algorithmic level, this is relevant. So for example, in my 2025 paper, there's like 2 assumptions in it. And one of them is about, the state is not somehow conspiring to break this optimization. Well, I forget what I named it. It's like assumption 2. And like no one has proven that this is correct. And I actually don't know how you would go about proving it. It seems like a difficult statement to prove. But if you had the quantum computer, you could just try it. And then you see that it would work.
In Google, I guess, is one of those places where you have access to like the hardware, and you can be like.
But not. I mean, for this particular assumption, you would need a cryptographically relevant quantum computer to test it. Yeah, you wouldn't be able to test it on a near-term machine.
So beyond this, the 48-bit integer factoring, are there other problems which you would think would be good to optimize in terms of?
I don't know if I'd say good to optimize, but good to know the cost of would be. There's other cryptographic, there's other cryptographies that are vulnerable to quantum computers.
Well, either cryptographies or maybe even broader.
Tasks, I mean, obviously, if we want to do chemistry simulations, it behooves us to make them cheap. And we do work to make that cheap. In fact, I mean, there's a lot of crossover between the two of them, because if you make an adder better, if you make the fault tolerance better, that benefits all computations that you want to do. There are also algorithmic innovations in chemistry. I'm not really so familiar with those. But yeah, I'm on a few chemistry like algorithm papers, and my participation was always of the style convincing the person who's writing it to just give me the circuit and stop trying to explain the integrals. And then I could look at the circuit and be like, oh, okay, they're trying to do a lookup and they're doing it the wrong way, and I can fix that. So yeah, it's absolutely the case that improvements to arithmetic and improvements to fault tolerance affect everything. And the beneficial use cases of quantum computers are particularly important to optimize, although most of my work has ended up being this broad stuff or like warning people about cryptography stuff.
Yeah, and to that end, the elliptic curve encryption underlying some of the cryptocurrency wallets, it seems like it's also a pretty impactful scenario. I think there are trillions of dollars worth of cryptocurrency currently in circulation, and how does the existing work sort of carry over to that problem?
So a lot of the stuff that's done for factoring is very specific to integer addition, or like this modular multiplication idea doesn't quite translate over very nicely. Chevignard et al., who are the ones who came up with that technique, they have put out a recent paper on elliptic curves, and they did manage to lower the space, but not nearly as much. And they paid a very heavy gate count in order to get that benefit.
But in terms of number of qubits, so it's mostly in terms of gates.
I think they estimated something like 3.1 times n qubits, but the number of gates was 1,000 to 10,000 times higher than other approaches. And in the context of fault tolerance, 10,000 times more gates kind of means you have to increase your code distance by let's say like 6 or 9, and that'll hurt you. That'll probably eat the savings in this case. But maybe someone can take that paper and they can build on it. They can fix the extra gates or something. We don't know.
But as it stands, it's a further milestone than RSA 2048. Like even
Oh, that's not clear to me. Which one will fall first? I don't know. The elliptic curve keys are much smaller, so the n that we're talking about is like 256 instead of 2048, and that's a major advantage in terms of the number of qubits that are needed. Because when I say 3 times n, it's 3 times 256, right, which is still less than 2048 divided by 2, so 1,000 instead of 700 something.
Yeah.
There are advancements being made on this stuff. We put out a paper a few months ago on a new way of doing multiplication and division. And one of the most expensive steps in the key operation that elliptic curve Shor's algorithm has to do is a division.
Mm-hmm.
So you take that, you can apply it, it'll get a little bit better.
How difficult is to do division?
The really tricky thing is that it's a quantum division. So you have a superposed number, another superposed number, and you want to divide them mod like the modulus of the prime field. And the only way that this involves kind of in computing the multiplicative inverse of the number. The way that people do this classically is by running what's called an extended GCD, extended greatest common divisor. And that's just a sort of many step process. Right. And you have to run that process under superposition to get the inverse, and then you have to uncompute that process because you created all this garbage along the way.
That's a Euclid's algorithm.
Yeah. Okay. Yeah, there's many greatest GCD algorithms. Euclid's is like the classic one from several thousand years ago.
Right.
There's also the binary GCD. There's the Bernstein-Yang GCD.
It's like once you know the period of the function and how you find the...
No.
That's a different one.
That is related. Like the post-processing of Shor's algorithm does use a GCD in the way that you're referring to in order to find the fraction that's closest to the measurement. But this GCD I'm referring to is happening as part of a division within the computation that's leading to those measurements ultimately.
So what do you see currently is missing, or the quantum computing community needs in terms of tools? And
I think people need a version of Stim or some variant that supports qubit loss, conditional Cliffords. I don't know exactly what that looks like, but there's clearly a desire for it, and people would use it. So generalize the ability for people to do circuit noise simulations to the types of circuits that people ultimately want to run instead of this restricted set that Stim currently allows. Another big software need is just better decoders. I don't even know if this is possible, but if someone could find, there was this decoder called BPOSD that was released several years ago. And this is sort of the default decoder that people go to now. It has various limitations. It can get stuck, it can fail to converge. It can, there's things that can go wrong. It has downsides. But it's very general. So it's a very good, I just want to try something and see if it's going to work type of decoder. If people could find other trade-offs in that space, that's probably good. Another example of such a decoder is called Tesseract. Tesseract is much slower than BPOSD, but it's also much more accurate. With Tesseract, it's very plausible that you run a shot and then it could decode for a couple days, or it might decode in a few seconds. It's highly variable runtime. Other pieces of software, I don't know if it's too early to really get into the compilation all the way from circuit down to fault tolerance, because we keep changing how we're going to do it. But that will clearly eventually be needed. No one's going to be making this stuff by hand. Eventually we'll have to get to the point where classical CPUs are, where no one person understands everything that's happening when you write some C code and then run it on a processor. It's just, there's too many optimizations along the way that took people their lives to make. Currently, we're not anywhere near that, but certainly once the actual machines exist that are doing these big algorithms, that stuff will start creeping in.
You mean compilation from the, let's say, abstract circuits towards the...
As well as the execution details of what happens at runtime.
Because I feel like there's also like several layers. The lowest level is like what pulses you send, like RF, microwave, or laser pulses.
As a very simple example, in the surface code, if we want to move a logical qubit from one place to another, we'll kind of like stretch out the patch and then shrink it down. We could instead set up entanglement between the two locations and then teleport. And setting up the entanglement is a process that you can retry. And so it gives you a little bit of error detection instead of error correction. And so something as simple as I want to move this from this place to this other place could like invoke all these little subroutines related to entanglement purification. And the user may never know about any of that. And they may not want to know. But I think that the execution details will become very, very, very complicated. Not initially, but gradually.
So if you would have unlimited resources in terms of like funding, people, what kind of problem would you jump on solving? In general, like what would you do?
And with unlimited funding, you don't have a decoding problem for finding interesting codes. Technically, you just throw unlimited compute at it. I guess you could do unlimited brute force search for codes. Maybe you should limit the amount of funding I'm allowed to use here to mere trillions of dollars, or else I'll go crazy.
Well, let's say maybe you would start building like a lot of quantum hardware, or like, I don't know, classical compute to...
I don't know. I mean, honestly, the way I work, I don't know like day to day what I'm going to work on. Like, I'm terrible at planning things out. I just try to work on what's interesting. And I'm very fortunate to have found a place where that is compatible with like having a job. Yeah, I don't know what I would do with a whole bunch of funding. Like a lot of the stuff I enjoy doing is about like reducing the resources required for something, not increasing the resources required for something.
All right.
That's right.
But I guess if we just follow the thought about brute force discovery of code, how would that work? I guess you still have to somehow constrain it to such that
with mere finite resources, you would have to be clever about how you're picking.
What's the existing infrastructure, like whatever we have now in the world?
Yeah, I don't know. This is not how I go about finding things out. Like I'm a very do it by hand sort of person. Like I'd be thinking about, is there some simple symmetry or some other like handle that I can use to find a code that's nice in some way, as opposed to searching for them.
Interesting.
Yeah.
Finding codes like handwriting.
Well, it might also be with the computer
tools, visualization tools.
Yeah.
I think that's really cool.
Yeah. I want to return to the subject of learning. I think this might be useful for audience who are interested in, I think no matter at which stage of career one is, like there's always an element of learning. Like even if you're leading researcher, you still have to stay on top of what's happening. So how has learning changed for you, like in the whole journey, right? From when you first start off like with quantum computing to now you have a very well defined set of things that you're working on.
I mean, one major difference for me is when I was learning, there weren't very good online resources. Like the Quantum Computing Stack Exchange did not exist. So I could go to like a physics forum and I could ask a question, they wouldn't know computing. And I could go to a computer science forum, I could ask, and they wouldn't know physics. And quantum computing is kind of at the intersection of these two things. So it's very hard to get help. Now I'm on a quantum computing team, so I can just like turn to my left or my right and get help for a question like that. Also, like places like the Quantum Computing Stack Exchange exist now. And also there are LLM tools now that I don't know how good they are at this, but if you ask them a quantum computing question while you're learning, it probably knows the answer. For a research question, that's probably a lot less reliable.
At least it knows the source to pull up.
Hopefully, yeah. And hopefully it exists.
Not the fake one.
Yeah.
Yeah.
I think the learning story is much better nowadays than it used to be. And, various companies have, competed with each other to get into like university curriculums, which has involved creating a lot of learning resources that people could use. You could definitely have a much less like stumbling path than I did, where I didn't know what a unitary operation meant for far too long.
Yeah. And do you feel like the stumbling was actually, I don't know, a necessary part for like knowing things very deeply, or do you think felt like there's a
don't know.
shortcut?
I don't know. I mean, certainly it made it sink in. I don't know if I would say it was necessary. There's a certain element of entertainment to doing it that way, where you finally figure it out and you're like, oh, okay,
Right.
and then you can tell people the ridiculous way that you learned it. And like these SketchUp diagrams, often what I would do is I would say, maybe I'm allowed to do this. Maybe like, oh, if it curls around that one like this, I can like cut it. Because I half understand these things and I'm not quite sure what's allowed, I'll try that. And then with that step, I gradually delete the entire diagram. And I'm like, okay, that's probably wrong. It's probably the case that if I want to do something, I don't end up with nothing. But then you come up with another rule and it doesn't delete the entire thing and it makes it a little bit smaller. And then you progress on to thinking about, okay, what is the justification for this? Or maybe you ask, or I would have asked like Austin back then, like, does this make any sense? And he'd be like, why would you do that?
But it seems like in history, there was like several interesting kind of discoveries, which started like from what if, like let's say even from the field where I'm coming from, it's like metamaterials. So there was like one scientist in 60s, he was like, what if permeability can be negative, because in most of the materials it's positive. And he just wrote the paper, left it, and 50 years later people started to make kind of non-engineered materials with negative permeability, like effective. But
interesting.
Sometimes it just starts from asking these questions, and then somehow later it may become true.
You definitely
never know.
You definitely hear these stories of people having some new representation of the problem, and then within that representation saying like, oh, I have a Feynman diagram. What if I rotate it 90 degrees? Is it still valid? Oh, of course it's still valid. And now it represents some different process. The same thing happens with these pipe diagrams. You can take them and you can rotate them 90 degrees. And now a time-like computation has become a space-like computation under certain constraints. And it corresponds to what's called gate teleportation. So normally gate teleportation is thought of as this thing that you have to learn that's kind of complicated to get your head around. But I turn this thing 90 degrees is not complicated to get your head around. So it's very easy to express those things in this different language.
Yeah, the sort of meta point from this is how you think about like how you think about investing time in different ideas. I felt like we kind of touched on it like before about like certain ideas getting obsoleted by others, and then so I felt like there is one extreme where one would have very deep conviction on an idea in spite of it somehow falling out of favor, and then just kept pushing on it, and maybe there's a gap of 5 years, 10 years before, or in the case of, let's say, in AI, there are people who had to endure like a period of sort of ignorance, like a period of low attention on their idea. So there is this modality of sticking to an idea with deep conviction, and then maybe at some point the whole field will converge around it. And then there's also the modality of kind of surfing the wave of the latest research, and then try to think about what's the next step. How would you like where would you place like in that spectrum typically?
I find that I'm very focused by the fact that I'm on a team that's trying to make a machine that's going to work. This sort of prevents you from completely surfing on the edge, because you need to turn it into something that someone could actually do. So you have, if it's on the edge and you want to say, let's do this, you have to turn it into like, here is the series of pulses you would send to the hardware ultimately. And so this does mean that there's a lot of speculative stuff that I don't participate in until it's a little bit more concrete. And then sometimes I'm a little annoyed by how speculative it is until it's a little bit more concrete, even though you have to go through the speculative stage first. I hope that I don't get too stuck on things that end up not being used. Like if maybe we never end up using the surface code. Maybe we use the color code, or maybe some of these non-local codes end up winning. But I mean, I don't know how to predict that ahead of time. All I really know how to do is like, pick a thing that looks interesting and try to make it smaller.
Right.
That's sort of my day-to-day strategy.
And probably a lot of the tools you accumulate along the way can still be useful for.
Yeah, there's often some overlap.
Yeah. So what would you say to like, I don't know, a high school student or undergrad who's just curious about, where to go in life or where to go in career?
Yeah, based on what you learned from your life.
Yeah.
What would you say yourself, for like, the people who are just starting?
Make cool things. I don't know, if I was talking to high school students, I'd probably try to convey what I think is cool about it. I don't know. I think quantum computers are, like, people mostly talk about using them to solve computational problems, which makes sense. It's a computer. But classical computers aren't just used for that. They're used to solve generic engineering problems. Like, how do you make a more efficient car? You put a computer in to manage the gas mixture in the pistons. And I think quantum computers will be used for that stuff eventually. And I don't know. I just find that very motivating. Like, this, we know that the whole world is described by quantum information at the fundamental level. And currently we can't really work with that type of information, not reliably, not with many, many steps. And quantum computers should fix that. Like, if you go to like a website that sells microcontrollers and accessories, like, they'll have all these different types of sensors and actuators, like thermometer, light sensor. They won't have the electron spin transducer because the computer can't store that information. It would be lost in the conversion process. And they don't have the the polarization, or the entangled polarization outputter, because the computer can't produce that state. But with quantum computers, that could eventually be fixed. And you could have something that would transduce an electron spin into the computer and then do many, many steps of computation for who knows what, and then turn it into a photon polarization at the end. I don't know why someone would do that, but it seems like a very basic capability that would be very useful. There are also, I think, concrete examples in engineering where people are working with information that you could think of it as a quantum computation. People get a little annoyed at me when I call it a quantum computation, but you can think of the mirror of a telescope as a fixed function quantum computer that it applies to the wavefront of light coming in. And people will make it a little bit programmable by having like these adaptive optics things that will adjust where the mirror is based on like some signal from a laser bouncing off the atmosphere. The reason they have to do it with the mirror instead of doing it in the post-processing is because something is lost in the conversion from the light into the digital information. And if it wasn't lost, if you could put it into a quantum computer with some sort of transducer, then you could apply the mirror in software or apply the adaptive optics in software. And okay, like, if you actually like work out the number of photons and so forth, this sounds completely insane. But who knows, 100 years from now, maybe in the same way that computers are everywhere in all of the sensors and so forth we have, maybe quantum computers are everywhere in them. So that's what I find very like motivating, is this like far future people using quantum computers for weird engineering things.
Yeah, opening the horizons.
Yeah,
for problem solving.
Yeah.
Whether it actually happens, I don't know. Yeah.
Well, that's cool physics. Okay, I think that was great ending. Thank you.